Okay, now that we've completed one entire normalization for the cataphorite sample, what I like to go through is just very quickly do some copying and pasting so that we can see how the different normalization schemes work for these different amphiboles. We'll quickly go through glaucophane, Edenite. You'll see that one actually, both of those show up twice. The magnesial hornblende. Then we will try out perhaps a couple of different normalization schemes here on the gedrite, ferrigedrite, and cursitite. And then finally, we will see sort of how our mystery amphibole turns out, and which normalization schemes work, which ones don't work, and what kinds of results that we get. So the beauty is that once you have this all set up the way that we have it set up here, the rest of it is really just cutting and pasting. And so what I can do here is that you can see that we've filled in all of these cells already, and we filled in all of the sort of test normalization routines that we want to use. And so at this point, we can just click on this cell and literally go all the way to the end here. And I'm not going to copy the amphibole name because that clearly is going to change. But all of the cells that have formulas in them, and I'm going to copy that, and I am going to put those here, put it here, and put them here. Okay, so our initial tests of amphiboles are all kind of worked out here. So let's check these out and kind of see how they all worked out. So again, none of them had any oxygen in the OH site because there was no titanium in here. You can see that even without iron, I'm off a little bit. So again, there's a slight sort of rounding error that's going on in here. It probably has something to do with my atomic weights. I may have a slightly different value somewhere that I'm kind of not expecting. But again, to 2 decimal places, these all look quite good. Okay, and again, the charge balances are excellent. There is no iron 3+, no iron 2+ in any of these. Again, because there was no iron in the original analyses. We can kind of go back here and see there was no iron in the original analyses, so there is going to be no iron 2 or iron 3. So let's take a look at our site fillings. Well, it looks like our site fillings look pretty good. We have 8 silicons, 0 aluminums, 7 silicons, 1 aluminum, and so on. And these look like they are pretty good matches for the original samples. Okay. Likewise here, as we look in the 6 coordinated site, here we have 2 aluminums and 3 magnesiums. That is a good match. Here we have all 5 magnesiums, again a good match. 4 and 1 matches, 5 and 0 match, and 3 and 2. So far it looks like we haven't made any errors in our formulas. Okay. Likewise, we'll go over here and take a look at our 8 coordinated ones. And the beauty is that among this first set where we only have calcium and sodium in the 8 coordinated site, you can see that we either have calcium and sodium, or sodium alone, or calcium alone. So this looks pretty good as well. And then finally, in the large 12 coordinated alkali site, we either are filled with sodium or we are empty. Keep in mind that in real life, we could have a number anywhere between 0 and 1. So we could have things that are 0.5, 0.25, 0.37, all sorts of different values. Okay. Again, our first set never had any fluorine in it. Since we didn't have any titanium, we didn't calculate any oxygen. So we have the full complement of 2 atoms per formula unit of OH. We looks like we have a bunch of all of our numbers work out well here. We see all of our totals are quite good. Again, I think we have probably a little bit of analytical error. That's probably why our totals aren't quite 100. We see 103. 99.99, but I'm really not too worried about that. That's, I think, within the analytical error here. I'll have to take a look at that later to see why that is. I'm sure I must have an atomic weight off somewhere by a couple of decimal places. Okay, I'm not going to bother going through the names of these things here because the names actually are the names that are written here. So let's take a look at some of these amphiboles down here. Okay, so I'm going to start off with Gedrite here, and I'm going to just copy the moles, the conversion from weight percent to moles. It's the first thing that I'm going to do. Okay, so we have numbers there. Now we have to decide which normalization factor are we, or which normalization routine are we going to use. So let's go through these sort of just systematically. Now, you could, if you wanted to, literally just test each of these and just see how they turn out. And in fact, we'll probably do that down here for the unknown mystery amphibole. But I think for these kind of first three tests here, we're just going to sort of eyeball this and sort of just visually examine which are likely to be good normalization routines and which normalization routines probably won't work. So the first one up here is 16, where all sites are completely filled. Well, if we look at the formula for Gedrite here, we see clearly that there is a vacancy in the alkali site. So there is no way that this normalization routine is going to work. And in fact, if we're just kind of interested here, just to kind of show you like what a failed result will look like, okay, I'm just going to copy just as far as the site fillings here and just show you how if you use one that isn't good, how you will get really bad numbers, okay? So here we have our kind of odd numbers here, and you can see that we're getting like 7.47, we're getting 53, and look at the charge balance. The charge balance is a value of 3, okay? And remember before I mentioned how, you know, if we're within about 1% or so, we can assume that it's, you know, a pretty good normalization. But if it's, you know, 5% or 10%, and this is, you know, between 5% and 10%, that it's kind of representative of a problem, okay? And we can see that the site fillings are incorrect. I mean, take a look at here. We're actually making 3 cations within this in this 8-coordinated site. There isn't even room for 8 cations. So clearly this is a problem. And so I am going to undo that and say that, you know, and just recognize that that one isn't going to work. Okay, so let's take a look at some of these others here. The next one is that 15 excluding potassium, so this disallows any sodium to be in A. Well, we don't have any sodium in this amphibole, so this one possibly could work. This one, you know, potentially could work quite well. And in fact, if we do a copying of this one, and again, I'm just going to do it as far as the site fillings here, and paste that in here. We see that we do get a good charge balance. It's pretty close to 0. We do get good site fillings here for the tetrahedral site. We get good site fillings for the 6-coordinated site. We get good site fillings for the 8-coordinated site, and we get a complete, you know, a full vacancy in here. So this one looks like it works pretty well. But is this the only one that works well? Well, let's undo this one. Okay, now this next one here says all sodium has to be in A. Well, again, there is no sodium in this. So this one, this normalization scheme, 15ENK, will also work. Okay, now let's take a look at this one. This one is 13ECNK, and it says that the the 4-coordinated tetrahedral site and the 6-coordinated site equal to 13, and no iron or magnesium is allowed to be in the 8-coordinated site. Well, we can look at the formula here and see that that clearly isn't going to work, because we have to have some magnesium, or if this were a mixed iron magnesium amphibole, we have to be able to put indeed a substantial amount into the site. And so again, I'm going to show you what this looks like, but keep in mind that it's going to fail. Okay, so here we have the site fillings again, and I will copy it in there. And okay, look at the charge balance, -6. I mean, that's just awful. That's close to 20% there. And we're getting all sorts of crazy. The tetrahedral site is underfilled. The 6-coordinated site worked well. The 8-coordinated site is underfilled. This is a very poor normalization. So these are the types of things that you want to keep aware of when you are doing your unknowns. Okay. So the last two here are forces all aluminum to be in the tetrahedral site. Okay, so you can see that one clearly will not work, because we do have aluminum distributed between both the tetrahedral site and the octahedral site, or the 6-coordinated site. This one says that this normalization scheme only allows silicon to be in the tetrahedral site, and it forces all aluminum to be in the 6-coordinated site. Clearly that one won't work either, because again, we have aluminum distributed between the two sites. And so it really doesn't matter which of these two up here I pick, because they're both going to be successful. And so I think I'm just going to pick the first one here. We tried that one out. It looked pretty good. And this time I'm actually going to copy it all the way across. And paste that down here. Okay, and again, we can just check it really quickly. Again, we have a good charge balance. We have good site fillings. And now we should have a fairly good total, exactly 100.01. Okay, so now let's take a look at our next mineral here, and our next mineral is ferrigedrite. Now we would expect that because gedrite, which is the magnesium end member, we were only able to use 15EK or 15ENK. Those were the only two we were able to use. That probably we would have a similar choice here as well for ferrigedrite. Now there is in this case, because I replaced all of the aluminum in the octahedral site with iron 3+, it turns out that maybe actually this 8SiAl will also work. But again, we already know the answer for this one. In real life, we wouldn't know the answer, and it very likely might not work in real life. But there is something interesting that I do want to show you here, because it's possible. Let's take a look here. Again, I'm going to just test this with the 15. And, oh, well, I probably actually have a bunch of nothings, because notice that I've forgotten to put the, I forgot to calculate the moles, so I got to do that first. So we'll put that in there, and so hopefully we actually have some numbers in here now. Okay, so check this out. We finally have some iron numbers. Okay, so we calculated normalized iron 3+ of 0.9989. That's pretty close to 1. And we calculated normalized iron 2+ of 1.0006. Okay, so that again is extremely close to 1. And if we look at the original formula that we had here, it was set up so that the irons would be 1:1. And indeed, the amount of iron 3 over the total amount of iron is pretty close to 1/2. Okay, so it's looking pretty good. Again, we have a good site filling here. We now have a good site filling here, and we can see we populated iron 3+ into here. We have moved the, we have our magnesium here in the 8 coordinated site. We have an all vacancy in the alkali site, and again, because we don't have any fluorine yet, we've calculated out the 2 OHs. I haven't calculated the totals yet, but I'm going to do that. This is going to be a little interesting. I'm not 100% sure how this is going to turn out. So you can see that we have produced some iron 3+, and we have produced some iron 2+, and indeed we have made a total of exactly 100, so it worked out quite well. Okay, so we have one last one to try out. And again, I'm going to, this time I won't forget, I will copy the formulas to produce moles in here, so we have that set up. Now, keep in mind, this is going to be the cursitite analysis, and so we're going to have some titanium in here, but we hopefully, if we've done this correctly, we are not going to have any OH in the OH site. We're only going to have oxygen, and we're also going to see later on that when we look at our sum of the negative charge, that you can see all of these have been 46, minus 46 so far, that this one should be minus 48 if we've done this correctly. Okay, now again we have to pick which normalization routine are we going to use. Well, you can see that we have all of the cation sites filled, and so this 16 should work. And if we look at some of these others here, this allows any sodium to be in A. Well, that one clearly would not work. This next one here, 15ENK, forces all sodium to be in A, so that one would work here. This one disallows iron and magnesium to be in the A coordinated site. Well, we don't have any, so that one would also work. And then it turns out neither of these two will work because aluminum is distributed between both of these sites. So I think for simplicity here, I'm just going to go with this top one because we already know that there aren't any vacancies. And I'm going to copy this one all the way across, again excluding the name. And paste that one down here. And let's see how we did. Okay, so again, we have a charge balance that's very close to 0, which is good. We see that we do have our minus 48. Again, it's slightly off a little bit, so there clearly is a little tiny bit of a rounding error, or I have a, I've rounded one of my atomic weights. We have the correct site filling in the tetrahedral site. We have the correct filling here in the 6 coordinated site. We have the correct filling in the 8 coordinated site. And we have the correct filling in the alkali site. And now this is going to be our moment of truth here. Yes, notice that we have no OH, and we have the full 2 oxygens in the OH site. Okay, and we've gone through and looked at the total here, and again the total is ostensibly 100%, 99.99. Okay, so all of these have worked out pretty well. So now we have the adventure of calculating or figuring out what our mystery amphibole is going to be. And the way that I like to do this is I typically will test all 6 normalization routines and just see which one works. And if multiple ones work, then we can kind of compare what the differences are between them. And so what I'm going to do here is I am going to go back and I'm going to start off with just the calculation for the moles. And put that in here. Okay. And why don't we just start from the top? See, at this point, I have no idea which one of these is going to work and which one isn't going to work. So we really have to kind of be systematic about this. So I'm just going to start here on this first one and copy this all the way across. And put it in, and let's take a look at how it looks. Okay, so our charge balance is 0.3. Okay, so that is a little bit under 1%. So it's not terrible. There's a possibility we might be able to do better than that, but we'll see. Okay, but at the moment, I would call this sort of marginally acceptable. We've calculated no iron 3 plus, but we have calculated some iron 2 plus. Now, the reason that this isn't 0 is clearly that this probably wanted to be a negative number, and because of our if statements, we forced this to be 0 instead of a negative number. And because it's not the original number that it wanted to be, but it's instead 0, is what threw this off a little bit. But that's good because that tells us that we kind of need to be paying attention to the quality of this normalization routine. So we take a look a little bit further here. We can see that, okay, well, this looks okay. We have some silicon close to 8. We put a tiny little bit of aluminum in here, but the bulk of aluminum we have pushed over into the 6 coordinated site. We have a variety of titanium and iron 2 plus and magnesium. Looks pretty good. We filled the site up with 5, so far I'm still happy with this. We take a look at the 8 coordinated site. We have a little bit of magnesium that spilled over, so clearly there was more than 3.64, and so we pushed a little bit over in here. We have a bit of calcium. We have some sodium. Fills it up to 2, which is good. We have 0.93 sodiums, a little tiny bit of potassium, and you can see that if we add 1 plus 2 plus 5 plus 8 up, we get 16, and it has to because that is what is required from the normalization routine. Okay, so let's take a look at our totals here. So we get 100.71 as our subtotal, but keep in mind that we have to subtract out a little bit of oxygen that's related to the excess because of the fluorine, and so it brings our total down to 100.13. So by and large, this is not a bad analysis. Okay, so I would take this as an acceptable analysis. But let's try out some other normalization schemes and see if we get something that we like a little better. And how do we judge something that we like better? Well, perhaps we will get a better charge balance. Perhaps we'll get better site fillings. Perhaps we'll get a better total. So let's take a look. And the way that I'm going to do this is I'm just going to copy this first part here. In fact, I'm going to copy all the way through the moles because we know this part isn't going to change. I'm going to copy this, and I'm going to put it a couple of rows down, okay? And so now, instead of the 16, I'm going to try this 15ENK, okay? So I'm just going to copy this all the way across. Oh, not that far, just to here. Paste that in here. Now let's take a look how it looks. Okay, so the charge balance is -2. So I would call that a unsatisfactory charge balance. And you can see now in this case, we've calculated all of the iron as iron 3 and no iron as iron 2. So you can see that picking a different normalization scheme actually changes the amount of iron 2 and iron 3 that you calculate. So this is one of the things that you kind of have to keep in mind as well when you're sort of selecting your normalization routine. But, and again, this number is so far off, probably in part because this really should have been probably a negative number. In fact, maybe even a very large negative number, and there are probably other problems with this as well. So let's take a look. The tetrahedral site looks like it fills okay. Take a look at the 6 coordinated site, way underfilled. Okay, that's a pretty substantial underfilling. So by and large, I can already see that I am not happy with this normalization scheme. So what we're going to do here is I'm going to get rid of that one, edit, undo, paste, and we're just going to assume that that one doesn't work. So I'm now going to skip down to the next one. Copy this one all the way across. And we're going to test this next one out. See if this one works. Okay, so let's take a look. And look at the charge balance. The charge balance is 6. That is clearly not a good analysis. I don't even need to go further in this to see that this is not a good normalization scheme to use. So we are going to undo that one. And we're going to test the next one. Okay. Okay, here we go. So let's take a look at this. Okay, charge balance of 0, so I really like that. And we produced some iron 3+, a little tiny bit of iron 3+, and roughly about 4 times as much iron 2+. So that's a pretty good analysis. That's, I think, quite typical for a lot of amphiboles, that we might have a essentially a 4-to-1 ratio of iron 2 to iron 3. So I'm pretty happy with that. We get a good filling here in the tetrahedral site, primarily silicon, but a little tiny bit of aluminum. We push the remainder of aluminum here into the 6 coordinated site. This finishes filling all the way up to 5. We don't get any iron or magnesium in here because, again, the normalization routine does not allow us to put iron or magnesium into the 8 coordinated site. But we do have sodium and calcium. It totals up to 2, which is good. We get a 0.81 filling for sodium in the alkali site, 0.07 potassium in the alkali site, and you see we even get a little bit of a vacancy, which is fine. That's completely acceptable. And again, you see that we've made essentially the same amount of OH, the same amount of fluorine, and the same amount of oxygen. And this is related again to the small amount of titanium that that's included in the analysis. So far I really like this normalization very much. Let's take a look at how the total works out. Okay, so the total is, still really very good. It's a little bit further from 100% than the previous one, but I'd say that this is sort of definitely well within the error of our analysis. I wouldn't I don't have any qualms about a 0.07 weight percent difference. So I like both of these so far. Okay. And I actually like the second one a little better because of the better charge balance. So if I had to pick one of these two, I prefer the second one. But we're going to do the same thing again here. I want to keep both of these so that we have like these all to compare. So I'm going to again copy the raw data plus the raw moles. And we'll put this now on the next line. And now I'm going to test this normalization routine right here, where silicon and aluminum are going to be in the tetrahedral site. Okay. Okay, so try that out here, and then we're going to do the same sort of check that we did a moment ago. Again, a horrible charge balance, minus 4.6. That's over 10% or essentially 10% off of what the charge, or the expected charge is. And so I would consider this a bad normalization routine. So we're going to get rid of that. And then we have one last one to try out, which is our all silicon in the tetrahedral site. Okay, and let's get to where we need to copy it, or need to paste it. We go there. So again, we have a charge balance that's off a little bit. It's 0.4. It's not terrible. It's within the sort of 1% sort of limits that I would consider this a sort of marginally acceptable analysis. It's not as good as our 13 ECNK normalization, but it's marginal. Okay, as you can see, we have 8 silicons because that is what we forced it to have. All of the aluminum has been pushed into the 6 coordinated site. This fills well all the way up to 5 cations. We see we get a little bit of magnesium in addition to the calcium and sodium. We fill up to 2, so that looks pretty good. Notice here in the alkali site that when we add the sodium and the potassium together, we actually exceed the occupancy of the site by 0.04, which is actually 4%. So not great, not terrible, but not great. Let's take a look at the rest of this. The anion site is ostensibly the same as in the previous analyses, and the analytical total we see is identical really to the first one. But I think with all of the problems in this analysis, the overloaded alkali site and the somewhat high charge balance, I would say that this is probably a subpar normalization. So I think that these are probably the best 2, and if I had to pick one, I would probably get rid of the first one, get rid of that, and the one that I like would be the 13 ECNK, which gives us a 0 charge balance. It gives us some iron 3 and some iron 2, and it nicely fills all of our sites, and it gives us a very respectable total. Okay, so this is how you normalize an amphibole. So I hope that you found this video useful. By all means, if you are feeling a little bit more, that you want a bit more of a challenge, go and take a look at my epidote normalization video, which already has all of the formulas built in, but it's somewhat more complex. It includes the peak overlap corrections. It includes estimates for REE estimation for the heavy rare earth elements in a rare earth bearing epidote, a number of other features. So do check that out if you're interested. And again, I hope you enjoyed this video, and keep an eye out for the next video I put together. Thank you very much.